Hey everyone, welcome back to Code 733Z. In today's video, we will go through a fascinating machine learning model that integrates variational autoencoders, VAE, cross-attention transformers, XAT, and Cox proportional hazard, COX-PH model. We will break down the code step by step, explaining how it works and how we use it for survival analysis on the lung disease dataset. Let's dive into it. Understanding the XAT-VAE-COX model. Before diving into the code, let's understand what this model does. XAT cross-attention transfer, a mechanism that enhances features learning by focusing on important relationships between data points. VAE, variational and autoencoder, a generative model that compresses data into a latent space and reconstructs it while preserving key patterns. Cox proportional hazard model, a statistical model used for survival analysis, predicting time to event outcomes, survival time of patients. XAT-VAE-COX model. This model combines these three components to learn meaningful latent represents while ensuring that the extracted features are useful for predicting survival outcomes. The lung disease dataset. We are using the lung disease dataset from the Lifeline library. The dataset contains information about patients with advanced lung cancer. It includes features such as age, the patient, weight loss, meal calories, Kearns sky score, a measures of the patient's ability to carry out daily activities, time, the time until an event occurs, status, whether the patient is alive or not. We process this data by standardizing the feature values and using it to train the XAT-VAE-COX model. Here, PyTorch library used for building and training neural networks. Pandas and NumPy handle data efficiency. Lifelines provide survival analysis tools, including the Cox models. Skit learning standardized data before training. Adam optimizer. Adaptive movement assumption is a popular optimizer used to adjust learning rates dynamically during training, making it well situated for complex neural networks. Cross-attention transfer layer. The class implements a cross-attention transfer Z layers. It uses PyTorch multi-headed attention to learn dependencies between input features. It improves features representations before feeding them into a VAE. Encoder with Z. The encoder is responsible for compressing input data into a lower dimensional latent space representation. FC1 converts input into a hidden representation. Cross-attention uses cross-attention to enhance feature learning. FCMU and FClogvar compute the mean and variance of latent space variance, crucial for variational autoencoders VAE to learn probability distribution. Section 6. Encode network. Decoder network. The decoder reconstructs the original input from the latent representation. FC1 converts latent variables into a hidden representation. FC2 maps hidden features back to the original input space. In a VAE, the decoder learns to generate data similar to input effectively, reconstructing samples from the compressed latent space. Cox loss function. The Cox loss function is used for survival analysis. It evaluates the risk scores of patient and ensures that the model correctly ranks survival times. Risk scores. These are derived from the latent space representation. A higher score means a higher risk of the event. Hazard ratio. .exp risk scores converts the risk scores into hazards ratio. Computes the cumulative sum of hazards ratio to evaluate the likelihood. Measures the probability of survival based on the ranking. Censored likelihood takes into account only the events where the patients actually died. Final loss, the negative sum of the censored likelihood normalized by the number of events. Loading the disease data. Loading the dataset retrieves the lung disease dataset from lifeline datasets. Dropping missing data ensures that the dataset has no missing values. Feature selections, age, weight loss, meal calorie, health status, level sections, time survival data, status survival. Standardizing features, normalize the data to ensure consistent scale, converting to tensors, prepare the data for PyTorch model. The functional load processes and prepare the dataset for training. Training the training function. Optimizer Adam uses Adam optimization for learning. Training loop for epochs in range epoch. Run the training process for a set number of epochs. Forward pass reconstructed input from the decoder. Latent space parameters for VAE. Z latency representation losses. Reconstruction loss measures how well the decoder reconstructs the input features. KL divergence encourages smooth and continuous latent space representation. Survival loss, Cox loss ensures the model correctly ranks survival risk. Total loss, sum of all losses with KL divergence weighted 0.1 factor. Backpropagation, total loss, updated model weights. This function trains the model by optimizing survival ranking and feature reconstruction. Evaluating the model, extracting latent representation, Z detach numpy converts latent vectors to numpy arrays. Creating data frame, data stores Z values and corresponding survival data. Cox model, Cox pH filter feeds the Cox model to Z features. Compute the C index, a metric indicating how well the model ranks survival times. Output, print C index, display model performance. A higher C index closer to 1.0 indicates better survival predictions. Running the model, initialize model, input dim, the number of input features, hidden dim, hidden layer size, latent dim, compressed representation size. Number heads, number of attention heads in the transformer, load data, retrieves and processes the dataset. Train model, train XAT-VAE-COX, runs training for 100 epochs. Extract latent representation model, retrieves encoded patient representation. Evaluate model. Z times events, computes C index to measures prediction and performance. Final thoughts. The code integrates Z cross attention transfer, enhanced feature learning, VAE, variational autoencoder, compresses and reconstruct data, Cox model, predicts survival risks. That is for today's video. We explored the XAT-VAE-COX model, walked through each function and applied it to the lung disease dataset. If you found this video useful, don't forget to like, share and subscribe for more machine learning content. See you in the next one.